Hey, how's it going? It's Miss Wesley back for a little bit more of using definite integrals to calculate volume of solids of revolution. We're in the volume packet, page 7 for starters, and you're going to see some examples that we've already covered where we revolved a region around a horizontal axis, the x-axis, and we were integrating everything here in terms of x. And what we learned is when you split this huge shape up into a bunch of disks all stacked up, you can integrate from one x value to another, and that will sum. If you integrate area, it'll get you to a total volume of that solid. So I want to look down to a question that we haven't tackled yet, new territory for us. Find the volume of the solid of revolution obtained by rotating the region that I see here in number 3. I'll shade this region around a vertical axis of revolution. I want to rotate it around the y-axis instead of the x. So get ready to think about a problem like this in a different way. We're going to be doing everything in terms of y when we get to these calculations. A joke to start things off is that I downloaded the Titanic soundtrack, but I can't listen to it yet because it's still sinking. All right, let's try this. So now we're thinking y's, right, instead of x's. In this shape, I can see a typical disc here, a circular disc. If you want to see an animation of how this is going to look spinning around a vertical axis of symmetry, I have it set up here. Here's the function y equals x to the third power. And we're about to revolve it about the y-axis. So here it comes. It's going to revolve around. We've seen this shape before, just oriented differently. And you're going to get this floodlight or bowl type of shape. It will not be hollow on the inside as is suggested by this graphic. It's going to be completely filled in, and we're going to go ahead and find the volume. So let's do it. On this typical disc, so the height of it, they'll call it usually delta x or delta y. That's going to be your dy. When we go to calculate the volume of this, and it's done in terms of y, we said, we're going to integrate from one y value to another. So here, instead of going sideways, let's go up and down from 0 to 8. 0 to 8. Which is given in the problem too. We're going to integrate area of a typical cross section, so a of y, with respect to y. That dy is just like that delta y that they call the height of that disk. Well, what would the radius of that disk be? It depends. The disks are going to be really tiny at the bottom of the shape. They're going to get wider and wider and wider, and the biggest radius we'll get out to here, I think, is going to be a radius of 2, will be the biggest that we get. Well, no matter where you are, right, the distance, the x distance out from the x-axis is going to give you the radius of that disk, of that shape. So what we should do here is, since we're thinking in terms of y's instead of x's, let's take this original equation and solve it for x. So if y equals x to the third, that means x, if I cube root both sides, equals the cube root of y. So we'll say the cube root of y is what we can use for the radius. No matter what, depending on where you are on the y-axis, the cube root of that number will give you the radius of the disk at that point. And we can plug this into an area formula for the area of this cross section. Use a circular area, a pi r squared. And then for r, let's plug in the cube root of y and square it because that's part of the circle area formula. Another way to write this that'll make it easier for us to take an antiderivative is going to be area equals, what would the power of y be? Well, the cube root of y squared gives you a 2/3 power. Okay, and we'll take this back up to the integral and see if we can work some magic here. We've got an integral from one y value to another, 0 to 8, up and down, of the area expression, so pi times y to the 2/3 taken with respect to y. And we'll use calculus from here. Leave the constant on the outside, so we'll just say pi. And now let's integrate y to the 2/3. It's got to go up a power. If we add 1 to 2/3, we're up to 5/3. And we'll also divide by 5/3. We'll multiply by its reciprocal of 3/5, evaluated from 0 to 8. Go ahead, do a plug-in. You can leave this answer exact in terms of pi, or you can leave it as a decimal. Both are fine. But you've got pi times 3/5 times the number 8 to the 5/3 power, minus pi times 3/5 times 0, right? We know 0 to any power is going to be 0 besides the 0 power there. So this is a little bit of simplifying. This is pi times 3/5. And 8 to the 5/3 turns out to be the cube root of 8, which is a 2, raised to the 5th power, gives you the number 32. Exact value volume is going to give you 96 pi over 5 units cubed. And again, a decimal approximation would also be just fine. Your example, so you've already tried some examples on page 8, and we're going to embark upon the page 9 examples today for homework. I was just thinking I would give you a head start on at least one of these questions, and I want to pick one of the ones where in this new format we're rotating around a vertical axis of revolution, so we need to use y's. So I was thinking of going for number 6. I'm looking at page 9, number 6, so we can draw the picture for ourselves, which we didn't have to do in the last question, and see if we could come up with the setup for an integral to find this volume. All right, so a couple dead giveaways that numbers 5 and 6 are going to be all calculated in terms of y instead of x. And the big giveaway is look how this original equation is presented. You're used to seeing a y equals some x expression, and here we've switched things up. X equals y minus y squared. Could you think back to your pre-calc knowledge of conic sections and think about which shape this is? I see a squared term here. I'm thinking some sort of parabola, right? And since it's the y that's being squared and not the x, I'm thinking it's a sideways parabola, and it is. It's a parabola that's actually going to open to the left. If I were to go ahead and sketch a graph of it, it's going to open in the negative direction. My disclaimer, these pictures, do not let them drive you crazy. They're just for you to organize your work, and they're not going to look perfect either. I just need some sort of sideways parabola. Now, since I'm working on this one with you and it's a little bit tougher, let's try the calculation ourselves. You know how if we had a parabola that opened up or down, we'd probably want to find some key points on that parabola, like x-intercepts, vertex would be good. Well, for a sideways parabola, maybe we could figure out the y-intercepts of this thing. And we know we do that. To find y-intercepts of any function or any graph, you can plug in 0 for the opposite variable. So if I set this whole thing equal to 0, 0 equals y minus y squared, I could do some quick GCFing to solve this and get where I'm going to have this thing hitting the y-axis. They are crucial here because when we do eventually set up a volume integral, we need to figure out, are we integrating from what y value to what other y value if it's not given in the problem. So let's solve this. Can you pull a y out as a GCF? And you'll have 1 minus y. We have two y-intercepts. One of them is at 0, and the other one's going to be, if you set this one equal to 0, at 1. And because we have so much room on this graph, I'm going to double the scale on the axes. I'm going to say 0 is at the origin, and let me just skip 2 tick marks and go up 1 to be right there. And you have these two y-intercepts, I should have said. So a y-intercept at 0 and a y-intercept up at 1. And you're expecting a parabola to go sideways through them. Yes, we could also find a vertex. For now, like I'm saying, it's just a rough sketch. And the big thing we figured out were these y-intercepts here, because now we know up and down, whenever we spin this thing, we're integrating from one y value to another, from 0 all the way up to where it gets cut off at 1. Now let's see if we can visualize this a little bit better. I want to shade the region in question. So here's the region bounded by that parabola and the line x equals 0, the y-axis. And our job is to revolve this region about the y-axis. We want to spin it around this, so can you picture it? The way I draw it is it's a little easier to draw it in 2D. So in 2D, here's a rough sketch. You're kind of like that from 0 to 1. Since you're going around the y-axis, could you draw me a mirror 2D image on the other side? So I want the mirror image like that. Doesn't look very three-dimensional to me right now. Sometimes when I draw in a typical disc, it'll make it look a little bit more 3D. So you get this circular disc shape in the middle of it. These discs are really tiny. They get big right at the center of it, and then they get tiny again at the top. I don't know, it kind of reminds me of like a Christmas tree ornament shape, possibly. Maybe this program will give you a better picture of it. Here's the original, right? Sideways parabola cut off from 0 up to the number 1. I want to revolve it, watch it go around the y-axis. You can see this better 3D version of it. It's completely filled in on the inside, and then you decide what you think that shape could be. Okay, so this is our task. We got to find the volume of this weird looking figure, and calculus to the rescue. We are integrating all with respect to y. I know I've been mentioning that a lot, but that's because we're revolving about a vertical axis of revolution. So here are some y values. What are we integrating? The area of a typical disk. Okay. Now the typical disk is going to have a radius of basically, if this is the x-axis going straight through it, the x distance is going to equal your radius. We want to figure out how far out horizontally we're going to get to each of the ends of those disks that would be stacked up throughout this shape. And in the original, right, we have x in terms of y. That's what we're fishing for. The radius is actually always going to equal the x expression in terms of y. We can use, kind of like in the last few questions, we can use the original function rule for the radius. That makes the area of a typical cross-section pi times r squared. So it'll be pi times this expression squared. This is what we're using. So go ahead, take that up to the original. Let's try to do the calculation together too. So we're integrating pi times y minus y squared squared with respect to y. And decide on a game plan. We could, I don't know, possibly try some u substitution. I'd say for this one, squaring a binomial is not the end of the world. Why don't we do some simplifying to make it easier to integrate before we have to do that? So let's get the pi out of our hair. We'll leave, imagine that, pi in your hair. We'll leave the pi on the outside of the integral symbol, and let's square the inside. So this gets foiled with itself. It's going to be the first term squared, y squared, minus double the product if we multiply the two of those. So when you FOIL it, minus 2y to the third, plus the last term squared, so plus y to the fourth. Getting rid of that power on the outside. Now I guess just integrate term by term, right? Leave the pi and integrate y squared. Integrate 2y to the third, so it'll be 2 over 4 y to the fourth. How about we just make that y to the fourth, 2 over 4 gives you a half, y to the fourth over 2, and then plus the integral of y to the fourth, y to the fifth over 5. Evaluate it from 0 to 1. End of the problem. You know, like we got through all the tricky stuff with setting up the diagram, and really this is huge, just setting up that integral of the area of a cross section. Now let's plug in 1 followed by 0. So pi times 1 squared over 2 minus 1 to the fourth over 2 plus 1 to the fifth over 5. So 1, and actually, did you guys catch my mistake right here? I was going a little bit too quickly. So hopefully you caught it, and this part should be y to the third over 3. Does that look a little bit better for the integral of y squared? Okay, so now that I fixed that, this first plug-in will give you 1/3, there we go, minus a half, and then plus a fifth. Minus 0 plus 0. So really just plugging in the 0 in this case is not going to affect the number that much. Your exact value answer, if you get that computed, is going to be, computed, I guess I should have said, going to be pi over 30 units cubed. You're always welcome to leave it as a rounded decimal. It's a very tiny number. Only a tiny bit of area here, or volume here, is going to be about 0.105 units cubed. All right, thank you for tuning in. I will talk to you soon. Have a good day.